Erin, hi, how are you?
Peachy Keen, how are you, my dear?
Good. So lovely to see you.
And you
I
as
do,
well.
yeah. I have been worried about something though. We told people that we had a rule and we didn't tell them why we had a rule. We just told them they had to follow us and listen to us. And like that never feels good.
I mean, sometimes it feels good to just be like, hey, follow my rules. But I see what you're saying.
Yeah. Specifically, a couple episodes ago, we said if you're doing elastic, use the small brush size and just do it. Like, we're not going to explain to you why in this video, just do it. So, figured probably be good to actually talk about why.
Sounds great. Let's dig in.
All right, I have a simulator for us today.
Ooh,
All right. Yeah. So today, let's not actually look at Elastic or talk about Elastic. Let's talk about sort of the principles that underlie Elastic. So Elastic, at least in its sort of normal mode, relies on a form of machine learning called a random forest. And I'll explain exactly what that means in a second. Essentially, a random forest is what if we make a bunch of decision trees and then we let the decision trees sort of make the decision for us. We have a whole bunch of trees, so it's a forest. And the random part of random forest means that what it does is actually subsamples the data and then makes decision trees with different parts of the data.
hmm. Okay.
So I have this cool notebook that is based on a plotting library that actually allows you to draw in some data. And so I'm going to actually draw in some data now that we can use to sort of make two classes and see how a random forest works.
I like this. Draw your own data. Like easiest way to a figure, right?
Yeah, use your powers for good. All right. So here I have two different classes. I can actually have up to four classes here, but I have my blue points and I have my green points. And I've drawn in some data. And I have about 50 to 60 of each. Um, and my random forest says that it can separate those with 100% accuracy, which
Ooh.
makes sense because, these are actually really different. Right now, my random forest is learning X position, Y position, and then the size, which is a pretend number that we can sort of assign. And right now, the sizes are all assigned as the same. So the sizes are not being really used by my random forest classifier. It's making all its decisions based on X and Y because the X is different and the Y is different. So that makes a lot of sense.
Yeah.
Um, and so what we can do is we can actually look at what our random forest is. So our random forest is actually 100 different decision trees. If I want, I can pull up any decision tree I want. So I can pull up decision tree 30 and I can see what that looks like. And in that one, it says if the Y value is less than a certain number, call it class 2, otherwise call it class 1. And we can look at just the first nine, and we can see that some of them start with X, some of them start with Y, some of them have one level, some of them have a couple of levels. But essentially, what this does is it then goes through for every data point, and puts it through all 100 trees, and then says, okay, in 80 of these trees, it says it's class 1, and in 20, it says it's class 2. The wisdom of the crowd must be right, and so therefore, um, we should call this class 1.
So it's not using any single tree to make a decision. It's saying like let's look at all of these trees. So in your example, right, like the Y value alone
Hmm.
gives us potentially lots of the information we need, but if we're looking at those points, we
Hmm.
need both X and Y values to be able to separate them. But
Hmm.
the decision tree, each individual decision tree contains not sufficient information. It's the collection of the trees, that's the forest,
Hmm.
that has like all of the information that we would need to separate.
No, I mean, so what you just said is a really good point. We don't, in theory, in this example, need the X or the Y, or and the Y, because it could be either the X or the Y, because I made a point to sort of make these on a diagonal.
Ah.
Um, if I didn't, if say I drew this so that now it's only the X uh, or the Y and the Y, like what if I do this? And I'm gonna, for reasons that I sort of explain later, just add a few more blue points here too. So now we do need the X and the Y.
Hmm.
And it still says like X and Y are both important. It's a little more weighted towards X now because we have a bunch of things over here. But you can see now our trees have gotten a lot more complicated
Ah,
because it really does need the X and the Y both in order to sort of figure out, is this related to, is this a green dot or is this a blue dot?
okay. So each individual tree, like in the first instance, each
Hmm.
individual tree, well, I guess on this one too, it's the same principle, is
Hmm.
actually saying, like this tree, I think I can distinguish between the populations using just the rules in my tree, but we
Hmm.
have our level of confidence
Hmm.
not, we're making our overall rules or our overall cluster designations
Hmm.
based on consensus between each of those different versions.
Yes, exactly. And so each tree, and let me go down to a single tree now. So we now have a little under 600 total data points. So the random part comes in where each of the trees actually doesn't have the whole information. So here, like, here's a random tree. It has 186, so it has about 30% of the information. And
Mm.
so that's part of how we get the trees to all look different is you say each one only has a subsample of the information. And so otherwise you would just get the same tree 100 times and it wouldn't actually be valuable. But by saying, all right, we're going to subsample the data, then we can get different trees each time and we can hopefully get more robustness in our overall classifier by because we're calling on sort of the wisdom of crowds here.
Nice.
Mhm. Um, So how does this actually relate to Elastic? And what the heck does this have to do with a pixel brush? I swear it connects. All right. So all of that is how random forest work. What on earth does this have to do with Elastic? Why are we talking about a one pixel brush? Like, what on earth is the relevance of how does a random forest work? Well, it matters because Elastic is using a random forest under the hood, and we have our, if we think about our annotations here, we can think of them just like the pixel annotations that we make in Elastic, in that each pixel annotation we make has a certain pieces of information, X, Y, and size, for example, here, but in Elastic, it's like different textures, different edges. Um, and it matters because there's some principles about how machine learning works that are sort of important to think about. Here's one of them. So we can't control, other than by turning some features on or off entirely, what the machine learning algorithm uses in order to make its decisions. It just makes the best decisions it can. So, right, so I have my X and Y, but they're done in a way that are a little bit confusing. Our trees are having to get pretty big in order for us to figure it out. What happens if I take a different variable, like say size, and I make size super different between one of our two classes? Um, so if I do this, our decision trees, which before weren't really using size at all because size was the same, are now 50% based on size.
Hmm.
And if we look at the actual trees, it's not that size is always necessarily the first one, but that if we ask it for feature importance, size is rated as by far the most important feature.
Hmm.
So if what I want to learn is XY position and size is different, tough nuggets. Like, the model's going to learn what the model wants to learn. The model's going to say, what is the easiest way for me to get this? Machine learning models, whether they're deep learning or non-deep learning, will always cheat in that sense. They will always just try to get the best answer they can. And so if what Elastic learns is that it should only learn things that are in sort of one image versus another image because it's way easier for it to learn that. That's what it will do. Um, the other thing has to do with sampling. So right now I have a couple hundred points each for sort of my blue and green. What happens if I try to sort of, I'm going to add some red points, and they're going to be different color than the green here, but they're going to belong to the same class as green. So the model should treat these as if they were uh, green dots, but they're different color for visualization point. If I'm going to leave the size the same so that the size is a bad distinguisher, but I'm going to put the red dots in the same place that the green dots are. In theory, that should make the model try to care more, less about size and more about XY position again, because, I'm telling it, no, you have this other class of things too. So let's see what happens when I do that. So it's now still saying that it's 43.7% based on size. Our trees now get super big and can eventually, with enough depth, figure out the difference between C and D, but they're not actually focusing on the thing that we think that we care about. We haven't actually changed, most of our model is still all about size.
Mhm.
And that's because only 10% of the things here are actually based on D. So I have 30 dots of D and 300 dots of C. So some of our trees only have a couple of red points total. Uh,
So this comes into maybe as like this fit in with the idea of them cheating, right? Like they can
mhm,
just ignore the red dots
mhm,
and they're fine. Because if there's only a couple, then if
mhm,
they still perform well on the other color, then like who
mhm.
cares about those couple of red dots?
Exactly. But because it's easy to get almost always the right answer, by just ignoring a really small class. Um, so let me do an even more extreme example. Now, instead of putting the dots here, I'm going to put the dots on top of the blue where they shouldn't be. Um, and if I only draw a few dots there, I have 400 dots of green and only 10 dots of red. It doesn't try to learn this at all. It just says, nope, okay, I have 0% accuracy on red, and that's fine.
Hooray!
Um,
Machine learning model goes, eh.
yeah, and now I have 10% as many, still 0% accurate. Ooh, I got up to 6% accurate now with like 75 versus 400, but you can see as long as there's mathematically more of points that look like this than points that look like that, the model is not really giving a crap about these points. It's getting 100% accurate here. Ooh, apparently that was a little slow to upload. Now it's up to 15%. Before it had been at about 7, but
Ooh.
it is definitely 100 versus 15. It doesn't care about these points as much as it cares about these points. Um, and that is the thing about the one pixel brush. If you, on your first image, color in a whole bunch of stuff with a big brush, if you now want to go to another image and say, actually, nuclei look like this in image one, but image two has a different noise model or it's just a little brighter or a little dimmer, and you start putting annotations, if you don't put near as many annotations as you did for the first one, your model ain't gonna care. Your model doesn't need to learn to care, because it can still be really accurate by ignoring your second image and only caring about your first image. Now, Elastic is really good. It does a lot of things to try to avoid this. And you can see that even here, we have like 5 or 6 times as many as much as C, and it is now at least trying to to learn the red points, but it's still doing a pretty crap job at it. Um, so if you use a big brush, you now have to use a big brush all the time. If you annotate a lot of points, you have to annotate a lot of points all the time. And what happens when you have like a rare pixel class where there's only 20 pixels of that thing in your whole image? Like maybe you'd want like a nuclear rim or something else that's like just a very small number of pixels. If you have 400 pixels in one image and 20 in the other, you can't ever make the model care about 20 equally with 400. You just can't do it. Models are going to learn whatever the heck they want to learn. And so the only way to make your model care equally about all of the images you tell it about and all of the things you tell it about is by telling them about it equally. And so that could be using a huge brush. If everything you want to find is big in all of your images and you don't mind spending a lot of time drawing, but you can also just annotate 10 individual pixels in each of a few images and be done faster and still preserve your ability to deal with rare cases because you haven't done this thing where you have 400 examples that look like this and only 70 examples that look like that.
I love it. So our rule isn't just to get people to be lazy because we love it when people are lazy.
We
As
do
lazy
love
as
that too.
we want work to be as lazy as possible. But like you've clearly shown us here, it's not just about being lazy. Like it's actually what's needed
Mhm.
to get out the result you need at the end.
Yeah. So you get a better result and faster. I mean, why would you not want to do that when it's like, well, it could be worse and slower or better and faster?
That does seem like a pretty easy decision tree there.
Yeah, I see what you did there. And of course, I want to make the caveat of here, my decision trees are based on three total things, X, Y, and size. And they're very simple things. And this is often kind of what the case is when we're doing fluorescence. When you start getting into very complicated things like EM, which is what Elastic is originally designed for, you might need lots more features and lots more examples. And then in that case, sort of using a somewhat bigger brush, but still using these underlying principles of thinking about what's in your training set and trying to keep it balanced across images and across visual appearances. Those are still good principles, but maybe you can use a little bit of a bigger brush. But keeping the principles of how random forests work in mind, will still tell you to do the least annotation that you can get away with because your model will be faster and it will be easier to retrain if you realize that there's something that it didn't account for later, which is often what happens. You did it on batch one, now you want to bring in data from batch two. Batch two is a little different. Do you want to spend the same 3 hours you spent in batch one, or do you want to spend the same 10 minutes you spent in batch one?
Love it.
Yeah. All right. So that was the rule. There was a reason behind the madness. Hopefully this helps you understand random forest better in general and also why we are so obsessed with Elastic's tiniest brushes.
I love it. And I certainly have a much stronger intuition about random forests now. I have always followed the rule because from my very first day in the lab, like the rule was made clear. This is the rule you follow. But pretty nice to be able to develop the intuition behind, what is actually going on in, the math behind the curtain, to understand why we are following this rule.
All right. Thank you so much. Have a wonderful day. I appreciate you hanging out with me while I do math simulations.
Of course. Thank you so much. This is delightful. And it is always nice to know why we're following certain rules. So this is great. Thanks, dear.
Bye.